Okay, we're happy to have Andrea Bianchi from Bonn telling us about, I forgot the title of your talk, but string topology and graphs.
Yes, cobordisms. Yes, sorry, I'm writing it now. Yes, thank you very much for the opportunity to give this talk. So I will present an approach to string topology via these things that I call graph cobordisms. So I will first introduce what I think, how I think about string topology. So throughout the talk, I will fix a ring R, and immediately I would ask anyone to stop me if you have questions at any time, and also if you can't hear, if you can't see. I might not be immediately aware that you cannot see part of the paper where I'm writing. Okay, so please interrupt me. So throughout the talk, so first of all, can you read? Can everyone read what I'm writing?
Yeah.
Can you reasonably read the title? And this is a letter R. And R is going to be a commutative ring, which is where we are going to take homology coefficients. And then I will also fix, for the time being, an R-oriented manifold. So M is an R-oriented closed d-dimensional manifold. And for me, string topology is the study of mapping spaces of the form m to the x. And by this notation, I will mean the space of continuous maps from x into M, where x is a space. Just any space. The main example to keep in mind, which is the one on which most literature, I would say, is focusing, is when x is a circle. Then we have that M to the S1 is the free loop space of M. Okay, this is, I would say, the example that is most studied. But for me, X, as I repeat it, can be literally any space. And what we want to study is the homology of these mapping spaces. And the idea is that the homology groups of these mapping spaces with coefficients in R for varying X. So we will fix M, but we will let X vary. They carry additional algebraic structure. So extra algebraic structure in the form of string operations. And among these string operations, there are three basic ones that I will list now. Three basic string operations. So the first one comes from naturality of taking mapping spaces in X. So if F is a continuous map from Y to X, then we get a continuous map M to the F from M to the X to M to the Y, and an induced map in homology. This is really no surprise, I suppose, but let me write it down. The second one is the first in which we see the importance of M being a manifold, namely having a fundamental class. So if suppose that Y is a space of a special form, namely is X disjunct union a point. Then we get a map in homology of the following kind. We start again with the homology of M to the X. And then we go to the homology of M to the X cross M. And to do so, we cross with the fundamental class of M. Now, M was supposed to be d-dimensional. And so I'm going to have a shift in degree by d. So this homological degree will become star plus d. And well, this thing is the same as the homology of M to the Y. And the third basic operation is the one due to Chas-Sullivan. So in this, they introduced it in a special case in which X and Y were a pair of circles and a graph of rank 2. But let me extrapolate the general construction. So if now Y is obtained from X by attaching a one cell. So as I say, the example is X is being two circles and Y is being a pair of classes, okay, where you have adjoined one cell. This is the situation for the Chas-Sullivan product as classically intended. Okay, so let's suppose that just we have some space X and we attach on one cell. Then up to replacing X up to homotopy equivalence, assume for simplicity that this map from delta I, so the boundary of the interval, into X is a cofibration. Okay, so that we can safely think of Y as just being X modulo these 2 points. Okay, there is a homotopy equivalence. Then here's the construction works as follows. We have a space of maps from X modulo delta I into, sorry, the space of maps from X modulo delta I into M is a subspace of the maps from M, from X to M, namely the subspace of those maps whose values at the 2 points given by this inclusion of delta I agree. I will write this in a diagram. Here we have the evaluation at delta I, and here we have the diagonal inclusion of M into M square. And what I'm saying is that there is a pullback like this. So 1 second, I will try to pin my video. So that yeah, I don't think it's working, so never mind. Okay, so we have this pullback square, and now the idea is that M is a submanifold of M square, and in particular, it admits a tubular neighborhood U inside M square. So this is a tubular neighborhood. A neighborhood, you get tubular neighborhoods of M to the X modulo delta I into M to the X. I mean, these spaces are infinite dimensional. They're not quite manifolds, but it's still true that this space admits a normal bundle inside this space. And this V is going to be essentially the total space of this normal bundle. So this is a pullback, and this is also a pullback. And yes, so as I say, M
Andrea,
equals
can
into
I
U,
ask a quick
which we
question?
think, yes,
Are you assuming
sure.
throughout your talk that these are smooth manifolds?
So I'm not assuming that these are smooth manifolds, and you will see towards the end of the talk that I'm actually not even assuming that they are manifolds, but just Poincare duality spaces. But at the moment, feel free to assume that these are smooth manifolds. So what I'm going to construct, I think, makes sense even for topological manifolds anyway. You can find a tubular neighborhood, and you can consider the topological normal bundle of M into M squared. Anyway, let's agree that they are smooth. If this is maybe this is easiest to follow. So let's take the normal bundle inside M square of M. This is what U is homeomorphic to, and then we want to think that M to the X modulo delta I also includes to V, which is supposed to be the normal bundle into M of M to the X modulo delta I inside M to the X. Okay, and what we can now concretely write is following a chain of maps of homology groups. We start with the homology of M to the X. We go from absolute homology to relative homology. From here, we use excision, and we go to the homology of V relative to, sorry, here I should remove M to the X modulo delta I. V minus M to the X modulo delta I. And now I can use the Thom isomorphism. And this guy is isomorphic to the homology in degree star minus D. Notice the shift in degree of M to the X modulo delta I, which, as I said above, is the same as M to the Y. And so this long composite gives us a map from the homology of M to the X to the homology of M to the Y. Okay, this was a bit more complicated in situation 2, but there is a similarity, namely in situations 2 and 3, we have a canonical map from X to Y, and yet we have a map from homology of M to the X to the homology of M to the Y. And the other similarity is that we see a shift in homological degree, once up and once down by D. Situation 1 instead is more contravariant and keeps the homological degree. Okay, this is qualitative analysis. But let's now look at these three situations and try to put them together into under a common denominator. And this common denominator is going to be the notion of graph cobordism. So here's a definition: a graph cobordism between spaces Y and X is a cospan of spaces. So there is Y, there is something in the middle called W, and then there is X. And then we also have an additional datum. So together with a finite relative cell structure on the pair W, X of dimension at most 1. So literally, this means that W is obtained from X by attaching a graph, and by attaching a few 0 cells and a few 1 cells. And Y maps to W by some continuous map. We make a picture. So here's my space Y, and here's my space X. So first of all, I enlarge X by attaching some 0 cells and 1 cells. For example, I could do something like this. Here I attach a loop. Here I attach another loop. Here I attach a disjoint point. And then we have an inclusion of X into this thing, which is called W. And then we have some map from Y into W. And the observation is that given a graph cobordism, we get a string operation of the following form. We go from the homology of M to the X, then we attach the zero cells. So by repeatedly applying the construction number 2, we go into the homology in shifted degree D times the number of zero cells of M to the X union zero cells. Now we do an operation 3 several times, and so we attach the 1 cells, and we land into the homology in degree shifted by D times the relative or the characteristic W relative X of M to the W. And finally, we do operation 1, and we land in the shifted homology of M to the Y. And this is, just combining these 3 operations into a single one. But now the idea is that we shouldn't just consider graph cobordisms as a set, but they should form a space. And the space of graph cobordism should give rise to higher string operations. Okay, so let me write down this goal. So introduce a moduli space of graph cobordisms from Y to X. Denoted MGRYX, together with a local coefficient system which I will call psi, and it's decorated by D, the dimension of the manifold, and by R, the ring on it. And the desideratum is that we can construct higher string operations. So a map from the homology of MGR YX twisted in this local coefficient system, tensor the homology of M to the X to the homology of M to the Y. Okay, and the more interesting we get this space to be, for example, not a set of graph cobordisms, the better this map would be. The more information we can expect it to capture. Okay, so this is one goal, but we can be more ambitious, and we can notice that graph cobordisms should have a composition. So if you have a cospan in which W is obtained from X by attaching some 0, 1 cells, and then Y maps to it. Let me write notice. If you have the following situation, you have Y maps into W, which is a cellular extension of X, and X, let's say, maps into W prime, which is a cellular extension of Z, for example. Then we should be able to make here a push out, and let's call this W double prime. And Y admits a map to W double prime, and W double prime is again an extension of Z where we attach twice a bunch of 0 and 1 cells. So we really want a category of whose objects are spaces and whose morphism spaces are these modular spaces of graph cobordisms. Okay, so we want, and since this has to be a category whose spaces form whose morphism objects form a space and not a set, what we really want is an infinity category, grcop of graph cobordisms. And some sort of functor out of it into, say, graded R modules, sending a space to the homology of M to the X.
Andrea,
This is roughly what we, yes.
Question, when you say R modules, graded R modules, do you mean derived? Do you mean chains? I mean, is the action that you're
Yes.
going to factor through chains, or did you write homology on?
So yes, so also in this case, I'm I'm trying to be elementary in the first part, but actually I mean chains, so derived categories, and I will make it I will make this clear in a moment. So at this point of the talk, I've already mentioned the scary word infinity category, and but this is the setting in which things are easiest to discuss. So everything is considered up to homotopy equivalence from now on, and everything is derived. I don't know. Everything is infinity categorical from now on. So let me say one word about the need for the coefficient system, which actually connects also to your question. So why do we have to expect the need of a coefficient system to compute the homology of this modular space, not just with coefficients in R, but in some coefficient system? Well, the reason is what we have experienced in cases 2 and 3. A single graph cobordism is supposed to be a point in the modular space of graph cobordisms, and it's supposed to give a class in H0 of the same space. But here we see very clearly that the map from the homology of M to the X to the homology of M to the Y is a shift in degree, and the same happens here. And what we want here is a plane map without degree shift. So if we put 0 degree here and we put star here, then we have to put the same star here. This is going against what we have seen upstairs, unless this psi coefficient system carries an internal homological degree. And this actually points to the fact that this idea will really be valid in homologically graded R modules, or even better in chain complexes. You should think of this as a local coefficient system of chain complexes. Even though we will see that for a discrete ring, it's actually concentrated in a single degree. So okay, so we have a vast program, and the next goal is to introduce this grcop. So I want to introduce grcop. This category of graph cobordisms between spaces need auxiliary definitions. So the first is the definition of the category of cospands. So I will denote from now on by S the infinity category of spaces. And by cospan S, the infinity category of cospands. So this one has objects being spaces, and the morphism from Y to X is a cospan of spaces Y WX, as we saw above, and composition is given by push out, and it is symmetric monoidal. By taking disjoint unions of spaces of cospans of spaces, pointwise disjoint units. Okay, so this is the first definition, and now the first attempt will be the following, to take a subcategory of this. So let me give this definition. So cospan GR of spaces is the subcategory of cospan S with all objects. So it's going to be a wide subcategory, but only those cospans Y WX, such that there exists some, let me underline this, it's going to be a property, not a structure. There exists some relative cell structure on WX, finite relative cell structure of dimension at most 1. Okay, so W is obtainable up to homotopy from X by attaching finitely many 0 and 1 cells. And this is a property, so we are going to select inside each morphism space, in here, some connected components of that morphism. So this is going to be, and I will comment on this later. Unfortunately, I would be very happy if I was able to do whatever construction I'm doing later for this guy, because this guy is much easier to define and to present. So Jargop is going to be a bit more complicated. But now let me give another definition. GR is the full subcategory of this guy spanned by, let me write in parentheses, spaces equivalent, homotopy equivalent to finite sets. So spaces that have finitely many components, each of which is contractible. Okay, this is a definition. Now, let me comment on the fact that this cospan was a symmetric monoidal category, but also this subcategory is again symmetric monoidal, and this is again symmetric monoidal. You just restrict. Okay, so an example here, an object will be a finite set, let's call it B. Another object could be a finite set A. And then we have in the middle a space that can be obtained from A by attaching 0 and 1 cells. And this is roughly the same as saying that in the middle we have some graph G. And then we have a map from A to G, and then we have a map from B to G. Okay, this is the situation in this GR. And at this point, I have to mention an important recent result due to Barkan and Steinebrunner, which is going to be the key result to all of the, well, yeah, to all of the constructions that we are making. And the thing that they prove is that GR, which is a symmetric monoidal infinity category, represents commutative Frobenius algebras. So in the abstract, I've written Frobenius / Calabi-Yau, and the reason is that there seems to be a debate which terminology should be used. So here we'll just write Frobenius for simplicity, but let me tell you what this statement means concretely, and then I will give you also remind you the definition. So this means that for C, asymmetric monoidal infinity category, we have an equivalence between the space of symmetric monoidal functors from this GR into C. And this is equivalent to the modular space of commutative Frobenius algebras in C. Okay. So this is a notion I still have to give what it means, but in a second I will give it, and then there is a natural notion of modular space of such data, and the theorem says that there is a natural in C, there is an equivalence between these two spaces. So let me proceed with the definition. Yes.
Can I ask a question? I'm not too familiar with how to think of commutative Frobenius algebras in an infinity category. Is there a more like properatic way I could think about these objects? Are these like controlled by the properat of Frobenius algebras, or a resolution of these or something?
So I would say that this very theorem tells you how to think about them.
Mm-hmm.
Somehow, I mean, it's a bit of a tautological answer, but a symmetric monoidal functor out of GR is the datum of. It's like what is a commutative algebra in a symmetric monoidal category C? Yeah. It is the same datum as a symmetric monoidal functor out of finite sets, right? So maybe I will write this. So it's compare to this thing, which is probably better known. Fana tensor from finite sets in this joint union into C is the same as commutative algebras in C. And let me spell this out. When I write commutative algebra, I mean the infinity categorical sense. So you might prefer to use the terminology E infinity, but so this means E infinity algebras if you prefer. Okay, so you have this equivalence, and basically if you have a functor, you evaluate at the singleton, and you get the underlying object of the algebra, and then the map of finite sets from 2 to 1 will give you the multiplication, which is commutative, and so on. Okay, and this is a similar kind of result. So let me tell you what it is, a commutative Frobenius algebra. So commutative Frobenius algebra in C is a pair of two things. There is A and there is T. So where A is an algebra, a commutative algebra, so it's a symmetric monoidal functor from Finn. And T is a map in C from A of the singles, A of 1 to the monoidal unit. An augmentation such that if you compose, you go from A of 1 tensor itself, you multiply, you get into A of 1, you apply this augmentation, you get into the unit. Well, this composite map exhibits A of 1 as its own dual. You might say it's a perfect pairing or non-degenerate pairing. So this is the definition that that gives meaning to this theorem. And so this GR is going to be key. This probably is going to be key for all of the constructions I'm going to tell about. But now we still have to achieve our goal to introduce this GR cop. So I will do it in 2 more steps. So I will first introduce another symmetric monoidal infinity category, which I call GRS. It's a space version of GR, but it's not quite yet GR cop. So this is the symmetric monoidal infinity category, described loosely as follows. So whose objects are of the form A maps to X, where A is a finite set and X is a space. So spaces receiving the maps from a finite set are objects. And the morphism from B to Y to A to X is a diagram of the following form. We have B to Y, we have A to X, and in between we put a graph cobordism from B to A, and the graph cobordism, I mean, what we want to be a graph cobordism from Y to X. And this is a commutative diagram such that W is the push out of G and X along A. So what this diagram is saying is precisely that W is obtained from X by attaching a graph along the specified finite set A. And then we have a map from Y to W. And unfortunately, we also have to carry on a map from the finite set B to G because we want to be able to compose things. So objects, I mean, we should treat this guy and this guy in the same manner. So this is a symmetric monoidal again by taking disjoint unions of pointwise of objects and of diagrams. Composition is given again by operating suitable push-outs. I forgot the main main requirement. So to write down at least. So this one should be push-out. This thing should be a morphism in GR. That is, B and A are finite sets, and G is one dimension, is a graph. And consequently, you also get that this thing here is a morphism in this, what is it called, cospan GR of spaces, right? Because X and Y are spaces and W is obtainable from X by, I mean, this push out witnesses the required property. Okay, so in fact, this category comes from comes equipped with functors. So we have by definition a functors G from GRS into GR, taking the top line and G prime from GRS into this cospan GRS. And this G will be relevant later, but this G prime, I just want to say it's not an equivalence. So this is a bit unfortunate, but that's how it is. So you can forget about G prime from now on. And the sad thing about this category is that it has too many objects. We would like a category whose objects are just spaces and not spaces with a map from a finite set. And to achieve this, we're going to operate a suitable localization. So So if you have a morphism in GRS, G, B, sorry, I think I messed up. Should be Y, G, A, W, X in GRS is idle if these maps are all equivalent. So if Y is equivalent to W and is equivalent to X. And then we define GRCOP as a localization of GRS at idle morphisms. Okay, so this would be our definition, and let me point out the following: that every object in GRS is connected to one of the form empty to X via the idle morphism empty goes to X equal X, A empty goes to A is equal to A, X. Okay, so there is always an idle morphism connecting any object to one of the form empty goes to X. So in this sense, after this localization, this object becomes equivalent to this other object, and so it becomes fair to think of objects in GRCOB as being just spaces. And then there is also another. Okay, so there is a definition. MGR YX will be defined as the morphism space from Y to X in GRCOP. And actually, a proposition tells you that this thing can be computed quite explicitly in terms of morphism spaces in GRS. And this is the colimit of the morphism spaces from empty to Y to A to X. And the colimit is taken over A in finite sets with a map to X. So what this colimit is telling you is sort of the best possible formula you can hope for this space. You take B equal empty. So you just forget about this map from B to G. And then among all ways to attach the same graph G to A, you make identifications. If you attach a certain graph along a certain finite set, but you're also able to attach it along, say, a subset, then the two possibilities are identified. This is what this colimit is telling you. And much time do I have? I think
like 5 to 10 minutes.
5 to 10 minutes. So let me go into let me state the three more results. So the next result is also due to Barkan, Steinbrunner, and somehow morally, I will say a word about it, is originally due to Galatius. So I will state it in this form of Barkan, Steinbrunner, and then I will comment. So the result is that if you take the class infinite space of GR, this graph cobordism between finite sets, what you get is omega infinity minus 1 of the sphere spectrum. Now, Galatius has proved a similar result in his work on stable homology of outer automorphisms of free groups. And right, this guy has to do with, for example, with symmetric groups, and so you see that from such a statement you can get something about homology of symmetric group versus those of outer automorphisms of free groups. The fact is that the category that Galatius defines is not quite this category of graph cobordisms between finite sets, but a mildly different category. And the situation is that Galatius category maps into Barkenstein-Brunner's category as a subcategory, and this map induces an equivalence on geometric realization. But this is something that one understands a posteriori, so to say. I mean, but the fact that both have the same geometric realization, I think there is no really direct argument for this. But anyway, the difference is really mild. Something like Galatius doesn't allow graphs with vertices of valence 1, and in here we allow everything. So, but this can be, I mean, using this result, we get that. Let me directly say the application. So get. Okay, let me say that for D, symmetric monoidal space, so an infinity space, let's say, have that symmetric monoidal maps from this GR into D are the same as the loops at the identity of D. And I will take now D equal to, okay, so from now on, R is a infinity ring spectrum. And I will write mod R for mod R in spectra. So you can think of this as the derived category of R. If R is discrete, and the pick R is again pick of mod R. So these are the space of invertible R modules. And the idea is to take D to be D pick. So that the looping of this symmetric monoidal space. The thing is that you can pick inside here, sorry, omega B pick is just pick. Right, because pick is group-like. And inside here you can take your favorite object, namely R shifted up by D. And this very point in omega B pick gives you, by means of this theorem, a functor from GR into D. So get a symmetric monoidal functor GR into B pick. This is symmetric monoidal. Now we also get one from GRS into B pick R by using the functor G, and then this psi dr, let's call this psi dr. And let's abuse notation and call this also psi dr. But then you also notice that this new functor sends idle morphisms here to invertible morphisms here. Well, because in fact this is just a group point, so every morphism here is invertible. So also get psi dr from GR hop into B pick. And now if you look at this last symmetric monoidal functor, what it really does is sends objects to the base point here, not so interesting. But on morphism spaces, you get maps of the form M modulo space of graph cobordisms from Y to X to pick R. And this thing is a local coefficient system on this guy valued in invertible R modules. This assignment is symmetric monoidal, so there is some compatibility between this local coefficient system, and this will be good when we take homology of these morphism spaces with these coefficients, as we will get functoriality and multiplication of homology and so on. And at this point, I think I will use the last 1 minute to state the main theorem. The theorem says that if M is an R-oriented Poincare duality space of dimension D, for example, because it's a oriented manifold, then there is symmetric monoidal and R linear. Let me say that by this I mean mod R enriched functor, which I call GFT, a graph field theory that depends on M, and it goes from something that I will write, and then I will explain what I mean. So GR-COP tensor psi dr, and I take the opposite of this, and the target is just mod R. So let me say what this guy is. This is supposed to be a category enriched in R modules, and so chain complexes of R modules. I think this is the right intuition. And its objects are supposed to be the same as those of GR-COP. So basically, here objects are spaces, and the morphism object, morphism module from Y to X is chains on MGR YX with this coefficient in psi dr. And what we will do is to send the space, what this functor will do is send the space X to chains on M to the X, and it will send and if we recover, and GFTM recovers operations, the basic operations 1, 2, 3, when you evaluate them on very basic graph cobordisms. Okay, so this is the main theorem, and I think I have exhausted my time, so I will stop here. Thank you for your attention.
Are there questions?